In addition to wanting to know how much of something I have in the sample, I oftentimes want to know what is actually in my sample. So sometimes I don't know the identity of the compound that I have, and I want to know what that identity is. One way to do that is to do experiments which allow us to calculate something called the empirical formula of my compound. So an empirical formula is the smallest whole number ratio of atoms or elements in the compound. So for instance, if I have the compound C2H4, that represents the molecular formula for that compound. Notice that I can divide each of these subscripts by 2 and have the smallest whole number ratio of carbon and hydrogen in this compound. So CH2 represents the smallest whole number ratios of carbon and hydrogen in this molecular compound. And so this would be the empirical formula for this compound. Furthermore, let's remember that if we know the molecular formula, or in fact the empirical formula of a compound, we can find the percent by mass of each of the elements in that compound. So let's see how we would do that. So remember that percent by mass, so percent carbon, for instance, would be the mass of carbon in the compound divided by the mass of the total compound. So I could use the molar mass of carbon. There's one carbon in this empirical formula, so 12.011 grams per mole is the mass of carbon, and it's combined with 2 hydrogens, and so carbon plus 2 hydrogens gives me 14.025 grams per mole for the whole empirical formula per mole. So if I take that and multiply by 100% to get that into mass percent, I will find that this compound is in fact 85.6% carbon. And now I can do the same thing for hydrogen. So percent hydrogen would be 2 times the mass of 1 mole of hydrogen, because there's 2 hydrogens in the formula. So 2 times 1.008 grams per mole divided by the mass of the full formula, 14.025 grams per mole, and then of course times 100%. And I would find that I have 14.4% hydrogen. Now notice that these 2 things add up to 100% as they should. So the trick here is that if I can go from the empirical formula to the percent by mass of each of the elements, then I should be able to go from percent by mass to the empirical formula. I should be able to go the other way around. So any experiment which allows me to calculate the percent by mass of each element in my compound will allow me to calculate an empirical formula, or to infer an empirical formula for that compound. So let's see how that works in a real problem. Let's imagine that we've done an experiment which provides us with the percent carbon and the percent hydrogen in a compound that contains carbon, oxygen, and carbon, hydrogen, and oxygen. And we want to know what the empirical formula is. So we know the percent carbon and we know the percent hydrogen. It's likely that we're going to want to know what the percent by mass oxygen is as well. And we're going to remember that our percentages have to add up to 100. So 100% has to equal 37.5 plus 12.6 plus whatever the percent oxygen is. So I can find percent oxygen by difference. So I just take 100, 100% and subtract 37.5 and subtract 12.6, and I find that I have 49.9% oxygen. So now I know the percent by mass of each of the elements in my compound. And for the empirical formula, what I want is the lowest whole number ratio of moles of each of the elements in my compound. So I know I'm going to need to go from mass to moles. So the easiest way to do this is to assume that we have 100 grams of the compound. Notice that because we have percent by mass, it doesn't matter how much of the compound we take, the percent by mass of each element will always be the same, no matter how much we take. So we can assume that we have 100 grams. So our first step is going to be assume 100 grams of compound. And if we have 100 grams of compound, and out of that 100 grams, 37.5% is carbon, then we know we have 37.5 grams of carbon. Likewise, we know we have 12.6 grams of hydrogen and 49.9 grams of oxygen. So to get from grams to moles, we just need to divide by the molar mass. So if I divide by the molar mass of carbon, in this case, because I'm looking at the grams of carbon, I will find that I have 3.122 moles of carbon in that 100 grams of compound. If I do the same thing for the hydrogen, taking into account the fact that the molar mass of hydrogen is 1.008 grams per mole, I will find that I have 12.500 moles of hydrogen. And if I do the same thing for the oxygen, recognizing that oxygen has a molar mass of 15.9994 grams per mole, I will get 3.119 moles of oxygen. Okay, so that's the number of moles of each of these elements in 100 grams of the compound. But what I want is the lowest whole number ratio. And so to get ratios, what I'm going to do is I'm going to look and determine which is the smallest number of moles, and that's the oxygen. And I'm going to divide everything by that. So if I do that, I will get the ratio of carbon to oxygen, the ratio of hydrogen to oxygen, and the ratio of oxygen to oxygen. So if we go ahead and divide each of these by the lowest, then we have 3.122 oxygen divided by 3.122 carbon divided by 3.119 oxygen, and we find that we have a ratio of 1.001 carbon to oxygen. And if we do that for the hydrogen, 12.5 hydrogen divided by 3.119 oxygen, we find that we have a 4.008 hydrogen to oxygen ratio. And then dividing oxygen by oxygen obviously gives us one oxygen for every one oxygen. So now I can see that for every one oxygen, I essentially have one carbon. So I can round this to 1. Every oxygen is one carbon. There's a ratio of 1 to 1. Every hydrogen, every 4 hydrogens is equivalent to 1 oxygen. So there's a ratio of 4 hydrogens to 1 oxygen. And so if I put that all together, I can see that I have 1 carbon to every 4 hydrogens to every 1 oxygen. And that is my empirical formula for this compound.